image. The discharge line of a compressor is always going to connect right there to that bottom port of your reversing valve. Always, okay? And then, you know, there's these sort of three fingers, 1, 2, 3, that come off the other side of the reversing valve. So if you have this bottom port, which is an inlet, and refrigerant's always going to discharge in there like that from our compressor, okay? And it's really the sliding gate is going to determine which way that refrigerant can flow through the valve. But another connection that's never going to change is the suction port back to the compressor. You're always going to have a suction line leaving the middle finger and going back this way. You see my direction of flow for refrigerant? Always. This is very important to remember. That's never going to change. That flow of refrigerant's never going to change. Refrigerant's always going to leave this middle finger and go through a suction line back to the compressor. The compressor is going to pump it up to a higher pressure and discharge into the bottom inlet port of your reversing valve. Okay? So that's something to remember right off the bat. Now, the way in which that refrigerant can flow really depends on the position of this main valve, which is made up of the sliding gate. And we're going to come all the way back to talking about the specific answer to the question in a minute, but this is a worthy discussion. The way that refrigerant can flow through here, for instance, in the discharge line, if this red dot represents refrigerant flowing through here, the position of that sliding gate is going to direct refrigerant around the sliding gate in such a way that it'll go this way. So let me pick a good color here so that this is very clear. I'm going to pick, let's say, purple. So these purple dots, that's a very big dot. Let me make that a little smaller. These purple dots here are going to represent refrigerant, which is moving out of my discharge line and into my reversing valve, okay? I think I'll even take me out of the picture so it looks even bigger for you. Now, the way I've drawn that sliding gate right there, you're actually going to have refrigerant flowing around the sliding gate and out this way, all right? And that is going to go always to a condenser. You're always going to discharge out of your reversing valve to a condenser. Now, whether the condenser is inside or outside the house, really, it depends, right? So it depends on the function, whether you're in the heating mode or the cooling mode. But I can tell you that you're always going to move out to a condenser. And then we know for a fact that refrigerant is going to go through a condenser, probably be liquefied, and I'm just going to draw a little line here. No, that lost that. It's going to be liquefied, so I'm going to draw through the condenser, and then probably a metering device. I'll just write MD for a metering device. And then it's always going to come back into this port, the opposite port here like this. And so my refrigerant flow, which I was using with these purple dots, will go like this. You see? And back in here. Now look at the sliding gate. The sliding gate, which is shaped like a crescent moon, is going to cup that refrigerant and swoop it around so that it goes this way. See, it's going to swoop through like this, and it's going to swoop around and back out this way, and then you're, moving back to your compressor. So I've drawn the sliding gate in a particular position because in the position it's in, it pushes refrigerant to a particular coil. I've got more drawings I'll do on this, but just for this question, I think it's important to understand. Now, let's just say I change the position of the sliding gate because the main valve made up of the sliding gate, it can be moved under the force of pressure to reverse the direction of refrigerant through the valve, which actually, in effect, reverses the entire function of your system to be either from heat to cool or cool back to heat. So now I'm going to do that. So I'm going to clean up my whole image, and I'm going to show you some things that stay the same and some things that never change. So these things can come out, this can come out, this can come out, all this refrigerant flow can come out. I'm going to take that out, take all this out, all this, this, and this. Okay, look what didn't change. What didn't change is the discharge into the bottom or lone finger of your reversing valve and the suction out of the middle finger back to the compressor. Never changes. That direction of flow and those pipe connections never change. So if you want, you can just forever call that the discharge line. And this can always be the suction line. All right, but if I move my sliding gate because I'm changing the operation of my reversing valve, and I'm not saying whether I'm going from heat to cool or cool to heat. We haven't got that far yet. All I'm saying is this can be shifted to there. Now, the minute that happens, because you've switched the operation of your machine, you redirect refrigerant to the reversing valve such that my refrigerant, which originally went this way out that port, if you remember, now my refrigerant is going to go this way. So follow my little purple dots. I'm starting right here. Here are my purple dots. They're coming up. Now they're pushed this way around the sliding gate. And you're going like that. And you're still going to discharge to a condenser because you always discharge to a condenser no matter what. And it's still going to go through a metering device, and it's going to go to an evaporator, and it's going to come back through this port here. And my refrigerant is going to move in the opposite direction, technically, through these two devices, opposite to the way I drew it before. So my refrigerant now is coming back, and then as it moves back here through the middle finger, as it moves back here through this finger, it's going to swoop around my little crescent moon, that sliding gate valve, and come back this way. So here's my flow. Discharge out in the middle finger. Sliding gate's in that position, so my refrigerant's pushed out this port. I go to a condenser, metering device, evaporator. They're defined by the direction of the refrigerant flow. I come back to the opposite end of the middle finger. I swoop around and back out the middle finger here to the compressor. All right? So just giving you a feeling for now of the movement of refrigerant and how it changes direction through the reversing valve based on the position of the sliding gate. So if we clear all this out now and go back to our original question, the question was that a heat pump reversing valve will have the following configuration. The following configuration is always going to be C, pilot on top, main valve horizontal. You just have to memorize that. That's the way they want you to think of it. The pilot valve is here. It is an electronic solenoid. The main valve is here. So this is sitting on top of a long horizontal main valve. Pilot on top, main valve horizontal. And without giving too much away, I want to add one more thing to that. The sliding gate, which moves back and forth in here, can't see it anymore because I erased it, but as it moves back and forth, it's happening as a result of changing pressures. But this little pilot valve is what changes those pressures. And we're going to get to that in upcoming questions. Okay, so the pilot valve is electronic solenoid valve. The sliding gate is just a moving little gate inside, which reacts to changing pressures on each side of it. All right, so let's go to question number 3. And we'll just keep adding layers of information to our heat pump discussion because I've got quite a few in a row on heat pumps. Let's try this one. A reversing valve in a heat pump, A, B, C, or D. Try that one.
Well, whatever the answer is, it's the opposite for train. For honestly, it's messed us up a few times.
Yeah.
Just a simple setting in their thermostat.
That's very interesting. So there's a generalized accepted answer here where we live that's not the same down in Texas either, by the way. So what we want you to remember for the C of Q is we had 7 students answered. Let's see what the results are. Seems pretty good. So that's pretty good. Yeah, 71%. So you're energized in the cooling mode. Commit that to memory. All right. And that's, based on the belief that you want a system to fail to heat. So because there's this electronic solenoid that can fail, which is the pilot valve on the reversing valve, if it fails, you want it to default to the heat mode. And that way you always have heat in cold weather in Canada, which seems to be a good fail-safe way to build things, right? In Texas, I've been told that they're designed the exact opposite way, and it's interesting. I'm not sure who made the comment, but Train has them energized to heat, I imagine. Is that true?
Yeah, unfortunately, just setting in their, I don't know if it's all their systems, but they're fancy communicating with,
All right, so for us, we're going to memorize energize to the cooling mode. And the easy way to memorize that is because we always want it to fail to heat because we need heat in emergency situations so pipes don't freeze. So that's pretty good. I don't think I need to add too much more to that discussion. Let's go to question number 4. We got 65 questions to do today, so we'll try to move here. Number 4, for a heat pump running in the heating mode, a high discharge pressure can be the result of what? And then what I'm going to do is let you try that, and then we'll do a little micro lesson on this. Oh, wow, you guys answered fast. Sorry. Okay, let's see the results. Let's see the results. Ooh, okay, so 10%. All right, that's all right. We are going to think about this by doing a little micro lesson. So here we go. Let's talk a little bit more about the heat pump. And the thing about, heat pumps, the way to think about them to be successful on an exam is the first thing you do is don't immediately think condenser evaporator. Always think indoor coil, outdoor coil. Okay? And then second to that, the direction of refrigerant flow will determine which of those coils is acting as a condenser and which one's acting as an evaporator. And that flow is determined by the position of your reversing valve, which is, of course, in turn controlled by whether your thermostat's set to heating or cool. Now, we know a few things. We know that, it's going to be energized. We're going to energize your reversing valve to make the system run like a traditional air conditioner. And if it's de-energized, it will run in the heating mode. So here's what's going on. Let's draw the components out just quickly here. So I'm going to draw a sort of oversized graphic of a reversing valve, if you can bear with me for a second. And it'll look something like this. Here's your inlet port down here. And I'm going to try to draw... Yeah, I'm not like the greatest artist, guys, but I'm just going to do my best here. Okay, so that's kind of like what it looks like. And, I am not going to draw the pilot valve on that. We'll get to the pilot valve a little later. I will draw the little sliding gate inside. So I wonder if I can just draw the sliding gate in purple. I'll just draw it as a semicircle like this. There, sliding gate. No, I don't like that actually. Let's draw it like this, and like that. So I'm just going to draw that little purple semicircle as a sliding gate there, okay? All right. Now, what do we have? We've got a compressor. Got to have a compressor. I like to draw my compressor down here. Keep it simple. COMP for compressor. That's easy. Reversing valve. Now I'm going to draw 2 coils. I'm just going to draw the coils as boxes if you don't mind. Obviously they're going to be, made of copper tubes and aluminum fins, but I'll just draw them as boxes for now to keep it simple. So I'm going to draw a box here and I'm going to call it the outdoor coil. Why? Because I know it's physically positioned outside, so it's always going to be the outdoor coil. What I don't know when we're talking about heat pumps is whether it's acting as a condenser or an evaporator. That's only determined by the direction that the reversing valve is pushing refrigerant through them, okay? But I'm going to call it the outdoor coil, and then I'm going to call one over here, a big box, the indoor coil. That seems fair enough. Indoor coil. So, most of us know that if the system's running in the cooling mode, for sure the outdoor coil is the condenser and the indoor coil is the evaporator, right? And then you have to remember, if you switch it to the heating mode, those functions reverse. Your outdoor coil now becomes the evaporator, your indoor coil becomes the condenser. And another thing to remember is, when you're talking about evaporators and condensers, you just have to think of one simple thing to understand their function. Evaporators, whether they're acting as outdoor coils or indoor coils, whether, their position is inside or outside, they always perform the same function. Evaporators absorb heat. That's it. Refrigerant in an evaporator absorbs heat from whatever sources around it. It could be water, it could be earth, it could be air. Condensers always reject heat to whatever sources around it, water, earth, or air. An evaporator will always absorb heat, condenser will always reject heat from the refrigerant inside the respective devices. Now we have some pipe connections that never change. Some of them I've already pointed out. Maybe I'll use, what do I want to use here? Let's use blue to represent discharge. We're going to discharge out of my compressor and always into this. Always, always, always. Right? You're always going to discharge gas out of your compressor into the little lone finger of our reversing valve. The bottom of the reversing valve, I always call it. And, we're always going to have a connection between the outdoor coil and the indoor coil. So I'm just going to draw this. I'm going to put a metering device beside it, in between them. Call that a metering device. You could have two metering devices with check valves. You could have a bidirectional metering device like a restrictor tube or an orifice or capillary tube or something like that. I'm just going to keep this simple for now and say we got a metering device between the two coils. And then we have pipe connections, right? You have to have a pipe connection that leaves here and goes into that. So you got that going on. Actually, I'm going to take the direction of flow away because we don't necessarily know the direction of flow. We're always going to have this coil connecting back here. And the middle finger is always going to have a pipe connection. I'll put a little jump there, which is going to be your suction line. This is always suction back. So these directions I'm sure of, the discharge and the suction, because their connections here to here never changes, and this return connection never changes back to our compressor. This is a physical pipe, physical pipe, physical pipe, physical pipe. So there's all of our connections. I'm just not drawing all the arrows in for refrigerant flow. But I can tell you this. If this was set in the air conditioning mode, which I'm going to draw this in the air conditioning mode right now. So I'm going to write here AC mode. And the sliding gate would be to the left the way I've drawn this. And I'll tell you why. Because refrigerant is going to discharge in and around the sliding gate. You see how the sliding gate directs it this way? I can't cross the sliding gate. I have to be directed around the sliding gate. So my refrigerant, now I'll put arrows in, is going to go this way. And if you want me to add those little refrigerant dots, so that you can see that flow, it's like that, in that direction. And so now, because the reversing valve always discharges to a condenser, it immediately means my outdoor coil is acting as the condenser. You see? Because the reversing valve is discharging to the condenser, my outdoor coil must be the condenser. Therefore, my outdoor coil is going to do its job of desuperheating, condensing, and subcooling the liquid until I have nice subcooled liquid leaving my condenser, entering the metering device, feeding my evaporator. The indoor coil is now the evap. Must be the evap. Has to be. This is traditional air conditioning. That's the A coil above your, furnace in the plenum. And so it's going to do the job of absorbing heat from the air blowing over it, and it's going to boil the refrigerant and superheat it, and then eventually that refrigerant will leave the evaporator here. So I put my arrow in now, I see the direction of flow, and what's my refrigerant going to do? It's going to enter the connection of the reversing valve, and the reversing valve sliding gate swoops it around. That's why we draw that as a little semicircle. Swoops it around and pushes it through the never-changing suction line, which takes my refrigerant all the way back to the compressor. So here's my air conditioning mode. Refrigerant discharges out. It's directed and discharged to the outdoor coil. That automatically means the physically placed outdoor coil is a condenser. Makes sense. Liquid, hopefully subcooled, feeds inside through my metering device, feeds the indoor coil, which is the evap, comes back this way, swoops through the sliding gate of the reversing valve and through the suction line. So there's my AC mode. And in order to be in the AC mode, we must have an energized pilot valve. The pilot valve is energized, which pushes that sliding gate actually to that position. Okay, so that's all great. But our question said, if we go back to the question, said for a heat pump running in the heating mode, a high discharge pressure can be what? Okay, why don't we redraw this in the heating mode now and see how this changes? Now, the physical pipe connections don't change in the heating mode. It's just the sliding gate is going to change its position and therefore change the arrows directing refrigerant through my indoor and outdoor coils. So I'm going to take away some of these annotations here, best I can without removing everything. I can add other things back. Yeah, see, those dots are hard to erase, but it's okay. I'll put them back in. No problem for me to redraw things, guys. Take out that arrow, take out that arrow, take out that arrow, take out that arrow. Some arrows change, some don't. Take out AC mode, take out the term condenser, take out the term evaporator. Indoor and outdoor coils don't change. Okay, let's make sure we draw the rest of our, oops, almost forgot. Gotta have an inlet, right? Right down there. And that's gotta have an outlet up there. Okay, so that's back. And of course, I still need my connection here. All right, so those pipe connections are there, but I'm gonna draw it in the heat mode now, heat mode, which is actually the way the image is drawn, the graphic image that goes with your picture. The graphic image with the picture in the question, which looks like this. So let me just enlarge that for a second. If you look at this little guy right there, I'm basically redrawing this image with, my animated version of it. And you can see the sliding gate down here in the heat mode is in black. It's pushed to the right instead of the left. But that means that my purple sliding gate, which I've drawn here, the purple sliding gate, which is left, I'm going to de-energize the pilot valve, which is going to make that shift right. So to do that, I'm just going to erase it and redraw it right here. Give it its purple color. It's going to be like this, like that. See, it's just shifted from the left to the right. That's all that's happened when we go in the heat mode. But this changes everything because my refrigerant, which is always discharging out the discharge line connected to my compressor, now it can't be directed to the outdoor coil like before. It has to be pushed this way because it can't cross the sliding gate. The sliding gate directs it this way, and so this arrow now goes like this. And now we're pushing into this. But because a reversing valve always discharges to a condenser, that means my indoor coil is acting as a condenser, C-O-N-D. You see? And my refrigerant flow is going to leave the condenser as a liquid. Now we're moving in the exact opposite direction through the same pipes, through my metering device, feeding the outdoor coil. The outdoor coil has been forced to become an evap. So because evaporators always absorb heat, we're absorbing heat outside, and condensers always reject heat, we're rejecting heat inside, which is what we want to do when a heat pump runs in the heating mode. We want to reject heat indoors to get heat. And then some things don't change. We're going to have our nice superheated gas leaving our evaporator. And what's it going to do? It's going to travel right into this outlet of our reversing valve, swoop around the sliding gate, and back out our suction line to return to the compressor so that it continue its cycle. So there's my direction of refrigerant flow now in the heating mode. So here's the thing. When you look at that question that only 10% of us got right, it says for a heat pump running in the heat mode, a high discharge pressure is the result of what? You have to say to yourself, okay, first, number one, which coil is the condenser and which one's the evap? Once you ascertain that, then you just apply your normal rules that apply for troubleshooting. Like what makes the head pressure high? That's what you have. Well, it's usually something related to the condenser, right? So in this question, when I see this, I know I'm in the heating mode. The first thing I say is, therefore, my indoor coil is got to be the condenser. Because in my mind, I can visualize it. I'm rejecting heat inside. only the condenser rejects heat. So my indoor coil sitting in the plenum above my furnace is the condenser. What's going to make high pressure there? Anything that restricts airflow across it. Just like when the condenser's sitting outside in the air conditioning mode. I mean, if it's a dirty condenser and it's an air conditioner, you know you're going to have high head pressure. That's because you're restricting airflow across it and trapping heat in the condenser. You can't reject heat. So if the indoor coil is now my condenser, just say to yourself, basic principles. Anything that prevents it from rejecting heat to the air blowing over it is going to make the head pressure high. And when I look at those options, B is the only logical option, because B says undersized ductwork. Yeah, if your supply and return air ducts are small in the house, you're obviously restricting airflow across the coil, which is the indoor coil. And when that coil acts as a condenser, you can drive the head pressure up. It's as simple as that. It's like a blocked coil. You know, a dirty air filter would do the same thing. It would give you high head pressure in the heating mode of a heat pump. Okay, so it's all about, just organize your thoughts when there's questions about heat pumps. Like I said, try to think indoor coil, outdoor coil. After that, decide the direction of refrigerant flow based on whether it's the heating or cooling mode. Then you know which coil is the condenser or the evap. And then just apply basic principles. And those basic principles, by the way, come from the chart that Sam emailed you, which I think I have a copy of here. Let me see, where is it? No, that's not it. Where's my little troubleshooting chart? This guy here. Everybody's familiar with that, right? This is like your standard system, how your high side pressure, low side pressure, superheat, subcooling, and amps are all going to change based on the most obvious, what would I call these? Abnormal conditions in a system. So in our question, we're talking about having discharge pressure here. Let's just highlight that. I would highly recommend everyone has this chart memorized if you already don't. And forgive me, I don't mean to condescend you. Maybe you do have this memorized because you're all experts in the field. But if you don't, I would recommend it. So here's your high discharge pressure column right here. I'm circling it in purple. And anything that makes the arrow go up, right, is going to be some source that causes high discharge pressure. So you could be overcharged. You could have a dirty condenser. See, there you go, dirty condenser. So dirty condenser to me is the same thing as restricting airflow across a condenser. It could be dirty. You could have a burned out condenser fan motor. You could have blocked grills, whatever. Now, if your condenser is inside the house and you have undersized ducts, that is the exact same thing as a dirty condenser because you're restricting airflow across the condenser. And therefore, your head pressure is going to go up. So, the final step to answering that question we just did really comes down to your basic troubleshooting chart, right? But before you can apply the basic troubleshooting chart, you need to know which coil's the condenser, which one's the evap, and it's as simple as that. So we got more questions that we can do like this. I know that took a little while, but let's really get our basics down when it comes to heat pumps. Okay, next question. Let's see some higher marks on this one. Number 5. Reversing valves in heat pumps always direct refrigerant flow. Think about this one. All right, let's see how we do. 8 students have answered, 10 have answered. Oh, 50-50. Oh, well, we did go up though. We did go up. So all of the above is true, which brings me to an important point about multiple choice questions, because I feel like 50% success is there's a reason for this. In order to get the answer correct on a multiple choice question, you have more than one task. Number 1, you need to select one option which you know for sure is absolutely true. So prove A, B, C, or D is true. Then you need to disprove that the other 3 options you did not select are untrue. really, it is only then that you can be 100% sure that you've selected the correct answer. So it's proved that one option is true, and if you have time and you have the capability, disprove 3 are untrue. In a worst case scenario, at least eliminate 2 possibilities and boil it down to a couple choices. And then you follow your gut instinct at that point, which is 9 times out of 10 correct, okay? One more strategy when doing a multiple choice test is don't go back and change your answers. This is a very common mistake. Usually when you go back and change an answer, you're wrong. The only time you should go back and change an answer is if you read a subsequent question on the test which clearly indicates the answer to a previous question in that question. In which case you have 100% certain knowledge that you answered a previous question incorrectly. But if you're just going on gut instinct, I highly recommend do not do that because your first instinct is usually correct, okay? So just a few little tips there that we have come by this knowledge through literally testing thousands of students, and all of the tests that we've created over 15 years of teaching have all been multiple choice. So we know the pattern and the trend, and students, how often do they say to us, I changed the answer? We're like, well, we told you, don't change the answer, okay? Unless you're really sure. So in this question, the answer is all of the above. Let's kind of ascertain as to why. I'll just break out to this view here. So we'll use the image to follow this. Let's look at A, because some of us did pick A. What happened to my results, by the way? Let's go back to that. Yeah, there we are. Was that that's our results. So, yeah, 30% of us picked to the condenser. Now, why? Why is this not the correct answer? Because you don't know, and I could see where maybe I misled you a little bit. They do always discharge to a condenser. They do. They always direct to a condenser. I'm okay with that being an option, actually. If it had said outdoor coil or indoor coil, then I can understand why it might not be true. But to say it, the reversing valve always directs refrigerant flow to a condenser is true. It actually determines which coil is the condenser. So I'm going to give you that one, guys, in A. Can we double check that? I would like to double check.
The fact that all of them are right.
What's that?
It's the fact that all the answers are
A, B, C are correct.
Oh.
That's how they get you. You see that one correct answer and you focus
You're
in
gonna
on
kill
it,
me
you
one
stop
day with
reading.
this.
Okay, obviously this is totally on me being a goof right now.
No, you did exactly what
I did exactly.
27% did. They picked the correct answer. I mean, they picked the first right answer.
Which is absolutely correct, and I forgot that the question
I
has
think
a
you're-
most correct
I
answer.
think you're exemplifying what you just told
100%
them
exemplified.
5 minutes ago. Disprove the other
Yeah,
answers.
throw something at the screen and hit me, guys, because yes, had I stopped right there and picked A, I would be wrong because B, B and C are also correct. So we are always directing to the condenser by virtue of the fact that the reversing valve determines which coil is the condenser. We're always coming back from an evaporator. We saw the connections on the pipes, right? And we're always directing it to the compressor, absolutely, through the suction line in the middle finger of the reversing valve. So the correct answer, most correct answer, which you should always pick, is D. So very good, most correct answer. My bad on that one. Let's go to number 6. Reversing valves and heat pumps always direct refrigerant flow. Try this one. All right, nice. Answers coming in pretty fast. That's good. We got 8 of us have answered, so I'm going to reveal the results and see how we do. Let's see. Hey, nice, 75%, good. And this one actually you can answer. Oh, that's an interesting little glitch on my screen. Never saw that before. When you look at this question here, it's easy to eliminate A and B. Because if you look at A reversing valve always directs refrigerant flow from the outdoor coil to an evaporator. That can't be true, because what if the outdoor coil is the evaporator, right? So that's why you just cross that off right away. It could be functionally the evaporator coil, so it can't direct it to itself. And the same goes for B here. When it says it always directs from the indoor coil to the metering device, well, that's not necessarily true. Because if the indoor coil is the evaporator, then it's not going to direct it to a metering device, right? So you can take that one out. And because A and B are not true, D cannot be true. How can all of the above be true? And just by process of elimination, you know it's from the compressor to the condenser, which was very clear in our image. That I'm not sure why my image is like that, but we can look at the same image here and see, you know, there's our compressor, there's our refrigerant flowing, and the reversing valve always directs it to a condenser, right? Always to the condenser. Compressor to the condenser, compressor to the condenser. So that's awesome. All right, we got to get some more questions going on heat pumps. Our percentages are going up, which I love. All right, a heat pump reversing valve typically uses the power of what to reverse its position? Just remind you guys again to make sure you're circling your answers as you go. And if there's any that you've missed, just put it in the chat and we'll make sure we put it up there for you. When you get a second, can we take a look at who's been doing the homework? Just in case. All right, 9/11, there we go. All right, how did we do on this one? I'm thinking definitely over 50%. Ooh, 30%. So this is one of those questions where you could just commit it to memory. But of course, memorizing it is never as good as understanding why the answer is A, system pressure. So we know that the sliding gate moves back and forth, right? We know there's a pilot valve and then a main valve, which is the sliding gate. And the main thing that moves the main valve is system pressure. Here's a quick little miniature lesson on why. So here's a graphic image of the reversing valve here in your question, and there's your solenoid coil, which makes up the pilot valve, right? I'll just write pilot. All right. Now, what's going on here? The pilot valve here is connected to the main valve body here vis-a-vis little capillary tubes. And I'll just highlight those capillary tubes like this. You see they're in yellow. You can see them in yellow. You got one here, you got one here. Where did that go? You got one here, and then you got one here. And what they're doing is making little connections from one area of the system to another. They're just little pathways for refrigerant to flow. And so, as an example, I'll just take out these little annotations now. In the position your reversing valve is in right now, which looks to me like it's in the cooling mode, that means that your solenoid valve, which has obviously some kind of little plunger on the bottom of it, what it's doing is it's allowing, in that position, refrigerant, which I'll draw as purple dots because the purple dots work. Refrigerant is going to flow like this through this little capillary here, and then the position of that valve seat from the pilot solenoid is going to allow those refrigerant molecules to flow this way, okay, through this capillary tube like this, and that's going to exert a pressure this way. So you're using system pressure. Let's do that in blue so it's very obvious. There's your pressure signal, which is communicated by that little capillary tube, and it pushes on the sliding gate, which makes the sliding gate move to this position, you know? Now, if you de-energize this solenoid, This valve moves down this way to the right, probably under the force of the spring returning to its normal position. And then what that would do is it would change the pressures through the capillary tubes, right? So, I mean, you could imagine, I can't make this move myself, but if this valve here, this little valve seat, was to move this way, then perhaps refrigerant molecules can now go through this capillary tube and maybe go this way and exert a pressure like this on the sliding gate, making the whole sliding gate change its position. So that's why we say that the pilot solenoid changes its position, which creates a disturbance or imbalance of refrigerant pressures on each side of the sliding gate, which in turn determine whether the sliding gate is going to be moved to the right or the left. So the main force moving the sliding gate is actually refrigerant pressure in the system, or as we call it, system pressure. So hopefully that's fairly clear. All right, number 8. There you go. A heat pump, for an air source heat pump to operate in the heating mode, the refrigerant, A, B, C, or D. It might help you to know that the graphic image with the question has clearly shown the reversing valve in the heat mode position, so the direction of refrigerant flow is correct. And this is all about heat transfer, basic physics, right? Heat energy measured in units of BTUs only ever move from hot to cold. If you remember that, answering this question should be fairly solid. Here, let's see the results. 9 students have answered. And by the way, Sam, are our missing students here now? Everyone accounted for? Okay, that's great. Yeah, let's see how we did. Hey, not bad. 50%. So let's break it down and figure out where we went wrong. We're kind of across the board with the, half the group. 20% choosing A, 10% choosing B, 20% choosing C. So worthy of a micro discussion. Maybe this time I take myself out of it. We just look at the image. So here is our heat pump correctly drawn in the heat mode, right? And so we know for a fact that the indoor coil is the condenser, because we're directing refrigerant to the indoor coil. The discharge from the compressor is being directed to the indoor coil, effectively making that a condenser. And the outdoor coil is our evaporator right there. And so what do we know? Okay, we know this. We know the indoor coil is going to have return air. A little delay on this. We're going to have return air from our furnace. Here, I'll draw a little blower here. There you go. And it's going to be pushing air, right, across our indoor coil. And the outdoor, what do we have? We have outdoor air, and outdoor air is going to be pushed across the outdoor coil under the force of that propeller fan. I know there's a fan drawn on the indoor coil, but my blower looks a little bit more realistic for a furnace here in Canada. Okay, so heat energy is only ever going to go from hot to cool. So we just have to ascertain now which of these statements make sense in terms of, the function of a condenser evaporator. Again, remembering that condensers only ever reject heat and evaporators only ever absorb heat. So if a condenser is rejecting heat, the medium it rejects it to must be a colder temperature. And if evaporator is absorbing heat, then the medium it's absorbing heat from must be a warmer temperature, right? Okay, so statement number 1 here. Is it true to say the condensing temperature must be lower than the outdoor air? Well, how is that even relevant? The condenser is inside. What do I care about outdoor air? You see how you could just cross that off right away? That makes no sense whatsoever. We're only concerned about the ambient air around the device. So we take that out. How about B? The evaporating temperature must be higher than the outdoor air. Okay, hold on a second. My evaporator is outside. That's true. And do we want the temperature of the evaporator? In other words, the temperature I'm boiling refrigerant at in the evaporator should be higher than the outdoor air? Not possible. You can't boil something like that. That means heat would leave the evaporator and go to the outdoor air. We need heat to come from the outdoor air into the evaporator, so therefore the outdoor air must be warmer than the evaporator temperature. When I say evaporator temperature, I mean the temperature the refrigerant's boiling at, in your evaporator. So that can't be true. How about C? Condensing temperature must be lower than the indoor air. Again, totally opposite. We need the condensing temperature to be higher than the indoor air so that it can actually reject heat to this indoor air, which is blowing over it, and then we can get heat inside the house. And I mean, by process of elimination, only D can be true, which is, yes, the evaporator temperature must be lower than the outdoor air. Well, that's because the evaporator is outside, the outdoor air is relevant. We're trying to boil refrigerant from the outdoor air, so our refrigerant's got to be colder than the outdoor air, so heat leaves the outdoor air and actually boils the refrigerant. All right? The basic principle, once again, is that heat energy goes from hot to cold. Condensers only ever reject heat to mediums that are cooler than them, and evaporators only absorb heat to mediums that are warmer than them. From mediums that are warmer than them. All right, I want to get at least to question 10, then we can take our first break. I know we've been rocking here, so let's try question 9. All right, defrost cycle. What do you think of this? What's the defrost cycle of a heat pump? All right, 9 students have answered. Let's see what our results are. From the group, much better, 56%. I don't mind that this group keeps getting around 50%. It means there's value in what we're doing. I know you're going to remember these things. This is just something you can just commit to memory. A, the cooling cycle with the outdoor fan off. That's it. Move on, right? Now, why is it that? Well, it makes sense. Because, first of all, a heat pump is going to require defrost, not in the air conditioning mode. Air conditioners don't need defrost, right? If you have frost on your evaporator coil in the air conditioning mode, that's an abnormal condition. Maybe you got low gas or plug filter or whatever. But in the heating mode, when you make the outdoor coil your evaporator, and it's operating in freezing cold temperatures in some cases in the winter, which is when you're trying to absorb heat, of course you're going to form frost. The temperature of your refrigerant is going to go below 32 Fahrenheit in order to absorb heat from the air that has to effectively be warmer than it outside. So frost is a certainty, which is why we need defrost on heat pumps when they run in the heat mode, because our outdoor coil will ice up, expected to. And how do we defrost it? Well, it's basically simple. The system initiates defrost. We'll talk about how that happens in subsequent questions, but defrost is basically, hey, switch the system back to cooling and turn the outdoor fan off, which makes sense because when you switch the system back to the cooling mode, your outdoor coil becomes the condenser, and condensers are hot. So that coil starts heating up from hot discharge gas from your compressor. And so we use that heat to thaw the ice or frost that's on our outdoor coil. And that'll, go on for an expected amount of time. And during that time, you would not want to be blowing cold outdoor air across a coil that you're trying to heat up. So that's why the system should turn the outdoor fan off. So basically your outdoor coil, which is acting as the evaporator in the heating mode, the system will just quickly switch it to the cooling mode, make it a condenser, heat it up, keep the fan off so that we can thaw the ice quickly, and then get back, boom, switch back to our heating mode again. Okay? Nice one for you to memorize there. And finally, number 10, before we take a quick break, there we go. Typically on the defrost cycle control circuit board, the installer can set a jumper to control the defrost cycle of a heat pump at what? A, B, C, or D? All right, I like this, and I think our results are going to be high here. We're certainly going to know how many of you are working on heat pumps, and 90% almost. Good job, guys. Right, of course, you have options to change it from 30 to 60 or 90, depending on your needs, and that's awesome. So, guys, good job. Let's take a little break. It's exactly 11:59. I'm happy with where we're at.